In the last video, we talked about multiplicity and how we could use the multiplicity and our x-intercepts to give a rough sketch of a graph. Now let's turn our attention to a couple of useful theorems. One is called the turning points theorem. So a turning point on a graph is a point where the function changes from increasing to decreasing or vice versa. And these points are what we call local maxima or local minima of the function. So one example of a turning point is the vertex of a parabola. If you think about a regular parabola, it comes like this. The vertex is right here. On this piece, it's decreasing because the y values are getting smaller. And on the other side of the vertex, so this piece, the function is increasing because the y values are getting larger as x gets larger. So the degree of this polynomial, y equals x squared, is, hopefully everybody knows that's a degree 2. And there's one turning point. So in general, and this is the important part right here, if f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. And vice versa is also true. If the graph of a polynomial function has n minus 1 turning points, then the degree of f is at least n. So for example, if we look at the function f of x equals negative 2 times the quantity x minus 2 times the quantity x plus 1, we know the degree of this polynomial is 2, because if we were to multiply this out, our largest exponent on x would be an x squared, or we can just count the number of individual x's. So therefore, we know the number of turning points is n minus 1, or just 1. So this is just another thing that will help us graph our functions. Now let's talk about end behavior. End behavior tells us what happens for large values of x or very small values of x. In other words, as x gets closer to positive infinity or negative infinity. And the graph of a polynomial function will resemble the graph of its leading term when the polynomial is written in standard form. And remember, each term of a polynomial is a power function. So, a little preview for calculus. We would say the value of f, so the value of the function, becomes either larger or smaller, depending, as x becomes larger or smaller, again, depending on what the graph actually does. So, if we were to take, for example, f of x equals x cubed, remember that looks like this, sort of. We would say f of x approaches negative infinity as x approaches negative infinity. And we would say f of x approaches infinity as x approaches infinity. So the negative infinity part they're talking about is what I just highlighted in yellow. It's what happens as the values of x become smaller. And the positive infinity part is this, what happens in green. So what happens to the value of the function as x gets larger. We also have another notation we use called limits. And so we might say the limit as x approaches infinity of f of x equals infinity. So this is the same thing as what's highlighted in green right above it. And conversely, for the negative part, we can say the limit as x approaches negative infinity of f of x equals negative infinity. That is the same as what I highlighted in yellow previously. So let's talk about the end behavior of a function at some point. First, though, we want to list all the zeros and the multiplicities. So remember, to find our zeros, we have x plus 5 equals 0, which means x equals negative 5. We have x plus 1 equals 0, which means x equals negative 1. We have x minus 2 equals 0, which means x equals positive 2. And we have x minus 4 equals 0, which means x equals positive 4. So we have 4 different problems there. So let's list the zeros and their multiplicities. So you try to do this, pause the video, and then you can restart it and see if you are correct. So I'm going to write all my zeros first. Negative 5, negative 1, 2, and 4. Okay, the x plus 5, which is where the negative 5 came from, has an exponent of 1, so its multiplicity is 1. The same with the negative 1, which came from x plus 1. The x minus 2 had an exponent of 2, so its multiplicity is 2. And the x minus 4 has an exponent of 1, so its multiplicity is just 1. Now, let's discuss the general appearance of the graph of the function. So the first thing to know is that the degree of a function equals the sum of the multiplicities. So let's add up our multiplicities here. We have 1 plus 1 is 2, plus 2 is 4, plus 1 is 5. So that means that we have a function of degree 5. That means its end behavior is going to be like x to the 5th. And what do we know about x to the 5th? It's an odd power function, so that means it's one of those that looks like the cubed Superman curve. And so for these, f of x approaches negative infinity as x approaches negative infinity. Oops, left out the negative, sorry. And f of x approaches positive infinity as x approaches positive infinity. So that's what the end behavior is going to be like. So if we wanted to do a very rough sketch of this, let's go back over here and find our y-intercept while we're at it. So our y-intercept is going to look like 0 plus 5 times 0 plus 1, 0 minus 2 squared, and 0 minus 4. So we have 5 times 1 times 4 times a negative 4, which looks like negative 80 to me. So what would this look like? Well, if we were just to graph it, we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we have x-intercepts at negative 5, negative 1, 2, and 4. We know that as x goes to negative infinity, so does f of x. So that means it starts way down here. It gets to this intercept. The multiplicity is odd, so it crosses. At some point it turns around because it has to get back to negative 1, so it's got a turning point up here. Comes back down. The multiplicity of negative 1 is 1, so it crosses there. And it goes way down here and crosses at, that's negative 80. So this is not to scale, just pointing that out. But then at some point, it has to turn around and have another turning point. Because it's got to get back up to an x-intercept of positive 2. So it's got another turning point down here. At the intercept of 2, the multiplicity is 2, so it doesn't cross there. It turns around and comes back down again. Sorry, I'm having a hard time drawing this. So turning point, turning point. So it's got a turning point at the intercept. And then at some point, it has to turn back around because it's got to get to this intercept of 4. And since it has a multiplicity of 1, it crosses there. So it's got another turning point here. So we had a multiplicity of 5 and we had 4 turning points. So we're in good shape. So that's kind of how this goes. And it's hard to graph these, especially when you have intercepts of negative 80. But we do the best we can. Alright, in the next video, we will look at how to create a polynomial when we're given the graph.